Hello, everybody, and welcome to Tuesday's class. We're going to continue with Chapter 3, and I just want to emphasize that, if I haven't already said it, that in Chapter 3 is basically the essence of statistics. The measures of central tendency are the most important things, because when you're measuring two different groups, two different populations, what you usually do is compare the means and look at the standard deviations and look at what kind of curve you have. Anyway, we're going to continue with quartiles, if you remember from the video in the last class. And we're going to begin with the upper quartile. And just a reminder, the upper quartile, sometimes called Q3, is a number dividing the third and fourth quartiles. And the upper quartile can also be thought of as the median of the upper half of the numbers. The upper quartile is also called the 75th percentile. It splits the lowest 75% of the data from the highest 25%. And you can find the upper quartile by placing a set of numbers in order and working out Q3 by hand, or you can use the upper quartile formula. If you have a small set of numbers around under 20, by hand is usually the easiest. However, the formula works for all sets of numbers, from very small to very large. And you may also want to use the formula if you are uncomfortable with finding the median for sets of data with odd or even numbers. So, in our example, we want to find the upper quartile for the following set of numbers: 27, 19, 5, 7, 6, 9, 15, 12, 18, 2, and 1. So the upper quartile formula is Q3 equals 3/4 times n, the sample size, plus 1, to whatever term it is. So the formula doesn't give you the value for the upper quartile, it gives you the place. So for example, the 5th place, like the 5th term, or 76th place. So to put the numbers in order, which makes it just a lot easier for you to calculate. And for very large sets, you may want to use Excel to place your numbers in order. Step 2, you work the formula. There are 11 numbers in the set, so Q3 equals 3/4 times n plus 1 term. It becomes Q3 equals 3/4 11. That's the number of numbers, plus 1, which is the 10th term. Sorry. Just go back here. Okay. And just, you all have the known, so you can just figure that out. You know what? I can, if you want to do this in Excel, I will do it during the office hours. Okay? So if you come to the office hours, remind me about that. Okay, thank you. So just want to go back here and I'll show you the video. It's more about the interquartile range, but it also covers the upper quartiles. Okay.
Moo Math, where we upload a new math video every day. In this video, I would like to talk about finding Q1, Q3, and IQR, interquartile range. This would be helpful when you're setting up a box plot or doing a box and whisker. And so you may be a little bit confused in finding these numbers. Step 1 in finding the Q1, Q3, and eventually the IQR is you'll need to order the numbers from least to greatest. Once they're in order from least to greatest, step 2 is you need to identify the extremes. Next, you will find the median of the entire data set. Step 4 is find Q3, or the upper quartile. And this is the median of the upper half of the data. You will only use the data to the right of the original median. Step 5 is find the Q1, or the lower quartile, and this is the median of the lower half. And finally, you will calculate the IQR, or the interquartile range, by subtracting the lower quartile from the upper quartile. So let's go ahead and look at an example and walk through these. Let's go ahead and look at the first data set. And here it is: 19, 25, 16, 20, 34, 7, 31, 12, 30, 22, 29, 16. Step 1 is you would go ahead and put them in least to greatest order. And to save time, I have gone ahead and done that. And if you'll notice, we have 7. You can see it, we start at 7, end at 34. Okay. Now we're going to identify the extremes. The extremes would be 7 and 34. And you can see why you need to order them from least to greatest, because it'd be just takes some of the guesswork out of finding the extremes. Next, you need to find the median of the entire data set. So what I'm going to do, normally I cross these off, but at the same time I'm going to put a mark here, mark there, mark here, mark there, mark here, mark there. And I will continue this until I get the median of 20. So 20 is the median of this data set. Okay. Now, step 3 is you will find Q3. Now, please notice, since we have an odd number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we will not include the median of the data set in the Q3. So what I will do is I'm going to go ahead and put a parentheses over top of this, okay? And so that is our Q3. And so now what we need to do is go ahead and find the median of this top set. And I'm going to cross this out, this, and this, and the median is 29. And now for Q1, I will do the same, except Q1 is the lower set. And I will mark this off, this one, this, and 16 is the median of the lower set. Okay, so now for the IQR, I take the median of Q3 minus Q1, so that would be 29 minus 16, which is equal to 13. Okay, and then the range of these numbers, if you need to know it, the range will be 34 minus 7, which is 27. Okay, so let's go ahead and answer these questions if we can. What are the extremes? They are 7 and 34. The median of the entire data set we found is 20. The Q3 is the median of this top range, and that is 29. The Q1 is this lower, which was 16. And then the IQR was 29 minus 16, which is equal to 13.
Okay, I just want to, sorry, I just want to ask, does everybody understand that it's relatively easy in doing the quartile range and finding the extremes, finding Q3 and Q1? Good. Anybody have a problem with this? Doesn't everyone has a problem, or everyone doesn't have a problem? No. Okay. I have a question, and I know you're only in the 3rd semester. Has any of your instructors talked about any kind of standardized tests in accounting? Have they mentioned anything like that? Okay. I only ask the question because if there are standardized tests that are in accounting that you apply to the data, usually what's going to be asked of you is finding the interquartile range, finding Q1, Q2, and Q3. But you can see that it's a pretty easy process to find this. Anyway, so just continue.
Okay, let's work one more set just to see if we get a handle of this. Okay, and I went ahead and placed these numbers to save a little bit of time in increasing order. So the extremes would be 65 and 100. Okay, next I need to find the median of this set, and I go ahead and cross these off. Okay, and when I get down to the end, you'll notice that we have two numbers, and that's 80 and 82. So the average of 80 and 82 is 81.5. Okay, that's just the average of 80 and 82.
So I just want to remind everybody, if you've got a range of numbers and they're even, what you're going to find is the two middle numbers, add them together and divide by 2, that's your median. If it's an odd number, then it's the one that's actually in the middle.
So now, since we do not have an odd number, we're going to go ahead and include 80 and 82 in the set. So next, I'm going to put a bracket around this. That is Q1, and Q3 is here. Okay, so again, what is the median? 81.5. That's the median of the data set. Q3 is I mark these off and I find the median of this top set, and that is 90. Okay, so that would be 90. And Q1 is, again, I check these off, finding the median of this bottom, and that is 70.
Okay, sorry everybody. John asked a question. I'm not sure what you're trying to say here. What if there is are you talking numbers in the data set and you have to find the median? Yeah, okay. A lot, we're talking like 100,000 numbers. That's a good number. Okay. You're not going to do this by hand. Okay. You can, hopefully the data set that you will have will be presented to you electronically, and you certainly can do it in Excel. What's easier is when you have a data set that is extremely large, you want to use a statistical application, okay? Like SAS or SPSS. Okay, good.
And then the QR is 90 minus 70, which equals 20. Okay. Okay, so that would be the IQR 20. Hope that helps you in finding Q1, Q3, and the IQR, interquartile range.
Okay. I'm going to go back to the PowerPoint. Sorry, I got to go flip back and forth. Okay. Sorry, it doesn't seem to fit there. Okay. Now we're going to look at the curve. So have people been taught or been told about the standard normal curve or the bell curve? Have you done this in any of your classes? Anybody or nobody? Yes, no? Amir, yes, you have? Okay. That's 3 people. Okay. In physics, you did it. All right. So you haven't approached it from the accounting perspective or data perspective. Okay. Usually what you want in your data set is for the curve to look like this. This is what's called a standard normal curve. And it's symmetric. You can also have what's called a skewed curve. And this is, this is a statistical process. So if you're looking at this, I know this looks like this is on the left side, but it is skewed to the right, which means it's positively skewed. So you have to pretend you're behind this graph and you're looking at it from that angle, okay? And this one is skewed to the left and it's negatively skewed. So in the example here, this has zero skewness, which means it's not going one way or the other. If you made a line, not a straight line, but a curved line, this would look like a bell curve, okay? And in this example, when you have a symmetrical curve, the mean, the median, and the mode are all the same. They equal each other, all right? In this one, where it's skewed to the right or positively skewed, the mean, the median, and the mode follow this. The mode is less than the median, and the median is less than the mean. Okay? This is a problematic curve. Why? Because it doesn't follow the standard normal curve where we know, we're going to talk about it later, when we talk about standard deviation and z-scores. This becomes very easy to interpret. This and this one are not so easy to interpret. So you don't want your data to actually look like this. No, you shouldn't throw out any data and you shouldn't make up any data to change the way a curve looks, because the curve is also going to tell you something. There's something going on here where there's more data here on this side, less data over here. And in this one where it's skewed to the left and it's negatively skewed, the mode is greater than the median, which is greater than the mean. You see the mean here to the left on the curve. Okay? Does everybody understand that? Any questions about that? Okay. No questions? All right, so let's look at the video.
So we're going to look at the relationship between the mean, the median, and the mode. If we look at a symmetrical bell-shaped distribution, which is one of those shapes we discussed in the last lecture, noting that on the horizontal axis you have your numbers, your data values in ascending order from left to right, and the height represents the frequency. Now over here we have...
I just want to mention something. When you have a bell curve like this, in basically all of nature, all of life, around 90% of data that you're going to collect is bell-shaped. And therefore, there's been a lot of analysis and evaluation of the bell curve, so that is what you want when you collect data, when you're going to look at your data, and it makes it a lot easier to analyze the data.
have small data values. Over here we have large data values, and in the center we have something right in the middle. Now, when you have a symmetrical bell-shaped distribution, the mean, the median, and the mode are all right at the center of the distribution, and they all have the exact same value when you're dealing with a bell-shaped distribution. So they're all in the center, and they all have the same value. There are some values less than the mean, median, and mode. There are some values, data values, that are greater than the mean, median, and mode. The mean, median, and mode is directly in the center. Okay, if we look at a skewed left distribution, here's a picture of skewed left. And remember from our last lecture, skewed left means that the tail is being pulled out towards the left. The mean and the median have smaller values than the mode, as they are influenced by the extreme small data values that occur in the left tail distribution. So here's what happens in a skewed left distribution. The mode contains the data value that appears with greatest frequency. So the highest frequency, noting that frequency is the vertical measure right here, the highest point of this graph represents the mode. So that's easy to spot. Now, what happens in a distribution if you have a lot of small data, or I'm sorry, most of your data values are occurring in this range, but then you've got some really small data values down over here. So imagine a distribution of incomes where most of the incomes were over $100,000, and then you had a few incomes that were in the teens and 20s. Now, what would happen to your mean because you have data values in the teens and 20s? Well, the mean would be down. Notice that here's the mode. The mean is going to be pulled out to the left because it's going to be made smaller because of these small data values down here that.
Okay, I just want to stop because I believe that I had mentioned to you about how income is generated on Canada Census. They look at the median because it's the middle, so you don't have the extremes pulling basically the curve. So if they use the mean in the Canada Census, you would have many more average salaries, or sorry, average incomes over here to the left side, which would skew the mean. Okay? Is there any questions about that? Because you would have fewer people on the right side of the curve here.
Are basically dragging it to the left. The median is also going to be pulled somewhat to the left, but not as far to the left as the mean. The mean is really pulled lower because of these low data values. Consider the calculation of, imagine your test score, imagine test scores that are all in the 80s, and then you get a test score in the 20s. Well, your mean test score is going to be pulled down lower because you've got that 120. And that's what's happening here. You've got low data values, which makes it a skewed left distribution, and those low data values pull the mean down towards the left, and it does skew the median slightly as well. Okay. The median is larger than the mean because the median is not influenced as greatly as the mean to the extreme small values in the left tail. Okay, let's look at the exact opposite, the skewed right distribution. The mean and the median have larger values than the mode. Okay, so here we go again, looking at a distribution where numbers are listed in ascending order from left to right. And again, the mode is the data value that's got the greatest frequency. So the highest peak of this distribution represents the mode. Now, the mean and the median are both larger than the mode, because they are influenced by large data values that occur in the right tail. So here we have the right tail, and in a skewed right distribution, the reason why it's called skew right is because there are a few data values up here that are pulling the distribution, pulling the tail to the right. So you can imagine a distribution of tests in the 70s, and then you get a test score of 100, which has the effect of pulling the distribution to the right. Okay, because of that test score of 100, the mean is inflated, right? Imagine you're adding up 5 test grades, all of which are 70, but the last one is 100, you're going to have an inflated mean. It's going to be greater than the other data values, the 70s, because of the calculation involving the 100. The median is less than the mean because the median is not influenced as greatly as the mean to the extreme large values in the right tail. The median is still greater than the mode because it's pulled to the right somewhat, but not as greatly as the mean. The mean is more greatly affected when you have data values in the right tail. Okay, the mean is not a resistant measure of central tendency as it is not resistant to the influence of extreme values of outliers. So we saw in these two examples that you can have a skewed left and skewed right distribution, and the mean is greatly affected by data values in the left or right tail. So Matt,
I just want to stop here. When you're going to, decide on your case study, and I mentioned it earlier, we'll mention it throughout the course, look at the data and remember, when you have outliers that are either too large or too small, they are going to affect your mean. They could actually skew your data to the right or to the left. So I encourage you to use the data that we have, but if you want to, find some other data, we'll have to go through that because you do not want to have skewed data, because when you do an analysis, it's already biased towards one or the other. Like you might, when you're doing an analysis, you might get a false positive, which means you get a significant result, or a false negative, which means you don't have a significant result when it really is statistically significant. So be wary of that with regards to the data. And, if you have a large data set, say with 10,000 data points, and maybe 100 are outliers either to the right or the left of the data, that's not going to affect the data. But if you only have 30 data points and 10 of them are outliers, it can affect the data.
imagine that you have a few very high incomes in a distribution where most of the incomes are low. Well, those few very high incomes are going to have a great influence on the mean, even if most of the data values are lower. The median is more resistant than the mean, as its value is not significantly influenced by data values, which can be considered outliers, regardless of how large they may be. So you can have a few large data values in the distribution. The median is not going to be affected as much as the mean will be. Okay, the mode is the most resistant measure of central tendency to outliers. So when we say outliers here, in this example, when you consider incomes as outliers, if most of your distribution is full of low incomes, and then you have a few numbers in the 200,000, 300,000 range, those numbers would be outliers. And the mode, though, is not really affected by those outliers because the mode is still the point of highest frequency, the number of greatest frequency. And since you only have a few of those extremely high incomes, they are not going to be the mode. Okay, so that was the mean,
Okay, stop there. Okay. So, and now we're going to talk about the geometric mean. Has anybody heard of the geometric mean? Or has anybody not heard of it? Nope. Has anybody heard of the geometric mean? Okay, this actually is a very important mean when it comes to finances. And it's used in the financial sphere more than it used in other spheres. Okay? And it becomes useful in finding the average change of percentages, ratios, indexes, or growth rates over time. So I don't know whether you've talked about this, but like the Toronto Stock Exchange, but it's not really. Like the Toronto Stock Exchange, the New York Stock Exchange, those are indexes, okay? And when you're doing a geometric mean, it makes more sense rather than doing an arithmetic mean. So it's used in business and economics because you're often interested in finding percentage changes in sales, salaries, economic figures such as GDP, which compound or build on each other. And the geometric mean will always be less than or equal to the arithmetic mean. And it's written as follows here. Okay, the geometric mean is equal to the square root. In this example, you receive a 5% increase in the salary this year and a 15% increase next year. The average annual percent increase is 9.886, not 10. Okay, so you take the square root of 1.05. Okay, that's your increase. And a 15% increase is 1.15. And the geometric mean is 1.09886. Okay, that's basically just the calculated formula. All right, it equals the square root of whatever you're trying to find and the number of things you're trying to find. So there could be like 3 raises in a row. You'd have, in this case, it's 1 times 2, the first increase times the second increase. You could have 3 increases, you could have 10 increases, whatever it is. And you find the square root of that. This is your geometric mean. So let me get to the video to show you. And you'll see that it applies much more to business, if not all of business.
Suppose a mutual fund has seen its share price rise by the following percentages during each of the last 6 years: 12%, 15%, 20%, 15%, 23%, and 35%. Find the average annual gain over.
So this is something, if you become a financial consultant or a financial advisor, somebody may have an idea, they're coming to visit you, and either you say, oh, well, this fund has done this well over this number of years, and you can show them the information, or they may ask you, find me the information on this particular item, and then you can calculate that. What you're calculating is the geometric mean.
For the last 6 years, and we'll use the geometric mean. The geometric mean is equal to the nth root. This is the notation for the nth root as opposed to the square root. This is the nth root. It'll be the 6th root in our example of the numbers in question, of the product of the numbers in question. X sub 1 times x sub 2 dot, 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 times the last one, x sub n. Here again, we have 6 numbers. Our numbers in this example are actually going to be 1.12 and 1.15. And the reason for this is because, let's take a look at the 12%, for example. We have a 12% gain, so that's 100% of the original plus 12% of the original. So that's 112% of the original, or of the...
Sorry, I just wanted to stop. I just had a question. Is there anybody in the class that does not have the BA2 Plus calculator, which is the financial calculator? Everybody has that calculator? Good. Does anybody not have that calculator? Okay. I don't know whether you were told in the whatever class you had that asked you to purchase that. That is the calculator that is approved by the Canadian Chartered Accountants Federation or organization. Okay? Sorry about the aside. But
year. So that is actually the number that we're looking at when you see these percent growths. You wouldn't, like if something were $100 and it increased by 12%, you wouldn't say it was just $12. You would say it was the new amount was $112. So 112% of the previous. Okay, so we will use these decimals. So I will put down the geometric mean, abbreviated GM, is the 6th root, because we have 6 numbers here. The 6th root of the product, 1.12 times 1.15 times 1.20 times 1.15 times 1.23 times 1.35. All right, 6th root of that entire product. And this 6th root can also be written as a rational exponent. So the product of all of these raised to the 1/6 power. So I'll write the product of those. That's 2.951439, rounding at some point there. Now, if you were to type this in your scientific calculator, you would use the caret key, that's the power of, and then parentheses 1/6. So just to be clear here, that is an exponent. The 1/6 is an exponent. So this caret key means to the power of. Now, the result that you get would be 1.1977. So that equals 119.77% of the original. So that would mean a 19.77% increase, average annual increase. All right, in Excel, I've got the numbers already written down here, the 1.12 and so on. The formula is actually geomean. So you would type in equals geomean. But in case you forgot that, or you're doing this later and you forget this, you can go to the function. So we insert function, and we're going to go down. We're in the statistical category of functions, and we go down. We just look for something that starts with a G. Here's something that looks like it, geomean. See if that's right. Returns the geometric mean, it says. So that looks good to us. Geometric mean of what? And Excel automatically chooses. It tries to figure out what you're going to do. It says B1 to B7. However, we only have cells B1 through B6. So while this is highlighted, I'm going to choose B1 through B6 and then say OK. And I get that number that we had over here, that 1.1977. So the average annual gain, I'll say equals equals this cell minus 1. And I've already formatted this cell as a percent. So I hit format cell and then as a percent to make it look like that right away. By the way, this is an older version of Excel. It's actually Excel from Office XP so that everyone can play along. And if you have a later version, absolutely these features are still there in similar locations. They might be in just slightly different locations. All right, there's an example of the geometric mean.
Okay, and I believe I asked this in the first class. Everybody has a copy of Office 365. If you don't have a copy, you know as a student you're entitled to get a copy. So just remember that. Okay. So any questions about geometric mean? All right. So moving on to another aspect of statistics, referred to as dispersion. How is the data spread out? Okay. And why do you study it in statistics? So the average measures the center of the data, and it is one aspect of observation. Another feature is how the observations spread about the center, because that's what you're looking for. Are they clustered around the center? Are they far away from the center? You want to know that. If the observations are close to the center, usually the arithmetic mean or median, you say the dispersion, scatter, or variation is small. If the observations are spread away from the center, you say the dispersion is large. And the study of dispersion is very important in statistics. If in a certain factory there is a consistency in wages of workers, the workers will be satisfied. But if some workers have high wages and some have low wages, there will be unrest among the low-paid workers, and they might go on strike and arrange demonstrations. If in a certain country some people are very poor and some are very rich, you say there's an economic disparity. This means that dispersion is large. Okay, let's look at the video on dispersion. Okay, this is a rather long video, so pay attention because this gets into the range, it gets into standard deviation, it gets into variance.
The secret of happiness is variety, but the secret of variety, like the secret of all spices, is knowing when to use it. Not only is variety or variation the secret of happiness, it is also one of the underlying principles of statistics. As researchers, we are interested in if the data vary, how the data vary, and ultimately, why the data vary. The first step to determining if the data vary is to summarize the data. You're probably familiar with measures of central tendency, the mean, median, and mode. Now, let's look at measures of dispersion, which help us understand the range and variability of scores in a data set. The focus of this video is to provide a brief overview of the most common measures of dispersion and provide more detail on two of those measures, variance and standard deviation. Fair warning, we will focus on understanding the concepts of variance and standard deviation, not how to calculate these statistics. That will be covered in a later video. Let's start with a brief discussion of measures of dispersion, which deal with the variability or spread, sometimes called the spatter, of scores. Measures of dispersion help us understand the range and variability of scores. For our example, let's turn to a popular website in my household called Rotten Tomatoes, which reviews movies on a scale of 0 to 100, or what they call the film's freshness level. Movies rated on the low end of the scale are considered rotten. Actually, Rotten Tomatoes establishes the cutoff point at 59%. If a movie is rated 59% or lower, it's classified as rotten. while those on the higher end of the scale, rated at 60% or higher, are classified as fresh. Unfortunately, I can't show you their cute images due to copyright issues. Here is the list of movies that Rotten Tomatoes identified as the 25 best Christmas movies, along with their ratings. Now, some of these movies I've never heard of, and some of them I personally wouldn't classify as a Christmas movie. Notice the scores. The lowest score listed for this data set is 80 for Batman Returns, which came out in 1992, while the highest score listed 100 for the 1940 movie The Shop Around the Corner and the 1942 movie Holiday Inn. This relates to the first three measures of dispersion: minimum, the lowest value of the data set, which in this case is 80, maximum, or the highest score in the data set, 100, and the range, which can be thought of in two different ways. First, as a quantity, as in the difference between the highest and lowest scores distribution. The range of scores is 20. And second, as an interval, with the lowest and highest scores as the range. The range is 80 to 100, or the scores range between 80 to 200, which could be written as 80, 100. That covers the first three measures of dispersion. The next three are interrelated: variance, standard deviation, and z-score. You calculate variance on the way to calculating standard deviation, and you need standard deviation to calculate the z-score. The first two, variance and standard deviation, with how the numbers are spread out, or how they vary in relation to the mean. These statistics relate to the entire data set. Z-scores, however, are used to standardize individual scores or data points so that we can compare them with other data points in the data set. You can think of z-scores as measuring a particular score's relationship to the mean in a group of scores. The rest of this video will focus on variance and standard deviation. First, let's learn the symbols for the two statistical measures, as that will help us in understanding how one can be used to calculate the other. And we'll start with standard deviation. If you are reporting the standard deviation of a population, you designate that with the lowercase sigma character, the one that looks like a little O with a tail on the top. If you are reporting the standard deviation of a sample, it's simple, a lowercase s. In some cases, however, you'll just see standard deviation denoted with an uppercase s. Here's the connection between the two. Standard deviation is the square root of variance. So the symbol for variance is the same symbol for standard deviation, but squared. Variance describes the extent to which values in a data set vary. It measures how far a set of numbers is spread out in relation to the mean. Are the scores spread out a lot, or are they all clustered together around the mean?
Okay, so I just want to explain this. If you look at, if you look at the first graph, you'll see that the mean is not very tall. There's a lot of data underneath this curve, okay? Which means there's a big spread in the data. If you can see the second curve, you see that the mean is relatively higher and the data is around the mean, okay? And the spread is not as much as the first graph, okay? Which means the data is centered around the mean, as opposed to the first graph where the data is not really centered around the mean. There's more data than other data, but it's not as much as the second graph. Any questions about this? Because this shows you the spread of the data. So can someone tell me what kind of graph would you rather have, the first one or the second one? If you're going to analyze the data, which one would be easier to analyze? Anybody else? Okay, everybody's incorrect. Oh no, Rashani, you're correct. It's the second one. You want more data around the center because when it's spread out, it makes it more difficult for you to interpret what's going on because there's no definitive mean. When a lot of the numbers of the data are around the center, around the mean, it makes it a lot easier because you want to see what's the data that are on the tails, on the left-hand side or the right-hand side, because this is going to tell you that those data that are on the tails usually will be statistically significant from the mean. When it's spread out, it's much more difficult because they're almost always the same. Does everybody get that? Should I explain it some more? Okay, so say you have some data, and the data goes from 1 to 100. And say you have a sample size of like 100. And the data is all over the place. It goes from 1 to 100, and maybe and you figure out the mean, and maybe it comes out to 45, but it's spread out. It looks like the first graph. Okay. In the second one, you've got a lot of data that's going from 40 to 60, maybe 80% of your data, means only 20% is on the right-hand side or the left-hand side. So the numbers are centered around the middle. Okay, that's going to produce a graph like the second graph. The first one, it really doesn't tell you if there's any kind of real differences between the mean and something on the right side, on the left side, because the spread is so wide and there's not very many numbers in the middle, as opposed to the second graph where there's more numbers in the middle and less numbers on the ends. So what you're looking for when you're looking at the graph is to have it look like the second graph, where there's more numbers in the middle and there's numbers on either the right-hand side or the left-hand side. All right? Okay, we'll just continue here.
The larger the variance statistic you calculate, the more spread out the data are. The smaller the variance statistic, the more the scores are clustered around the mean. And a variance of 0 means that all the scores in a data set are the same. They are the mean. Standard deviation is the most frequently used measure of variability. Consider word choice, a deviation from something that is standard. In this case, the mean is the standard. Standard deviation explains the average distance that individual points are away from the mean. Not surprisingly, as standard deviation is the square root of variance, the larger the spread of numbers, the larger the standard deviation statistic. Let's look at standard deviation in more detail to understand why it's helpful. Assuming you have a normal distribution, the mean would of course be in the center. As the whole curve encompasses 100% of the scores, this means that 50% of the scores in the distribution are higher than the mean, and 50% of the scores are lower. Another way to say it is that the probability of a score being above the mean is 50%, while the probability of a score being below the mean is 50%. At the mean, the standard deviation is 0. In a normal distribution, the probability is that 34% of the scores are within one standard deviation above the mean, and about 34% of the scores are within one standard deviation below the mean. Added together, this means that there is a 68% probability that a score is within one standard deviation of the mean. The same.
Okay, we'll talk about it further on in the course, but it's important for you to be aware that the two dotted lines represent one standard deviation above and one standard deviation below the mean, and accounts for 68% of the data. This is in a standard normal curve. Okay? When you have a standard normal curve, there are a lot of attributes that you will already know. And this is one of them that you should be aware of. And usually, unless you get a false positive, the data that lies within one standard deviation above the mean and one standard deviation below the mean are not statistically significant from the mean. Okay? It's usually, and she'll probably talk about that after, anything that's above, but anything above 2 standard deviations and certainly 3 standard deviations is statistically significant data.
The principle applies to 2 standard deviations from the mean. There is about a 95% probability that a score lies within 2 standard deviations of the mean. Well, actually, to be precise, the 95% probability is that a score is within 1.96 standard deviations of the mean. And the same principle for 3 standard deviations, which would encompass virtually all of the scores in a normal distribution. Now again, to be precise, there is a 99% probability that a score lies within 2.58 standard deviations of the mean. All of the standard deviations to the right of the mean, as they are higher than the mean, are positive, while all of the standard deviations below the mean, or to the left, are negative. Let's see how this works. Assume we have a mean of 42 and a standard deviation calculated at 12. The mean, of course, goes right here in the very center of the distribution curve. Now we have to do a little bit of addition and subtraction. If one standard deviation is 12, then 2 standard deviations would be twice that, 12 times 2, or 24. And 3 standard deviations would be 3 times 12, or 36. So we can plot all of these starting with the mean. The mean is 42, and when adding one standard deviation score of 12 is 54. So a score between 42, the mean, and 54 would be plotted at 1 standard deviation above the mean. We can do the same for 1 standard deviation below the mean. 42 minus the 1 standard deviation score of 12 is 30. So 30 gets plotted at 1 standard deviation below the mean. This means that, assuming the scores are normally distributed, 68% of the scores are between 30 and 42.
So I just want to mention what she also mentioned. Unless otherwise specified, either in a test or some homework, you should always assume that you are dealing with a standard normal curve, that it looks like the curve that you see on the screen, okay? And then you can make the regular assumptions about the mean and the standard deviation. So only if it is mentioned that it is not a normal curve must you take other processes to evaluate the data.
Or plus or minus 1 standard deviation of the mean. Let's continue for 2 standard deviations. The mean of 42 plus 24, 2 standard deviations, is 66. So we can plot the score of 66 at plus 2 standard deviations. And the mean of 42 minus 24, or 2 standard deviations, is 18. So we can plot the score of 18 at negative 2 standard deviations. Now, assuming the scores are normally distributed, about 95% of the scores are between 18 and 66, within plus or minus 2 standard deviations of the mean. One last time for 3 standard deviations. The mean of 42 plus 36, the score for 3 standard deviations, is 78, which is plotted at plus 3 standard deviations. And the mean of 42 minus 36 is 6, which is plotted at minus 3 standard deviations. Remember we said earlier that, assuming a normal distribution, 99% of the scores are within plus or minus 2.58 standard deviations of the mean? If we use this as the multiplier, we would take the standard deviation of 12 and multiply it by 2.58 to get 30.96. That means that 99% of our scores would be between 11.04 and 72.96. Let's see what happens with the same mean but a smaller standard deviation, such as 1.5. The mean is still in the very center of the distribution curve. Let's figure out all the positive standard deviations first. The mean of 42 plus 1 standard deviation, or in this case 1.5, is 43.5. The mean plus 2 standard deviations, so 42 plus 3, is 45. And the mean plus 3 standard deviations, so 42 plus 4.5, is 46.5. And we can plot these numbers at plus 1, plus 2, and plus 3 standard deviations, respectively. We can do the same for the negative standard deviations and plot those. Now you can see that the scores are much closer together. There is less variation, and we can see what the likelihood is that a score will fall within certain parameters. This, then, is the value of standard deviation. Okay, let's add an example that will hopefully take all this statistical stuff and make it more relevant. Let's say that you are considering going to a movie and are split between 2 possibilities. 30 of your friends have seen both movies, so you ask them to rate each movie on a scale of 1 to 10, 10 being high. Knowing what you do about measures of central tendency, you calculate a mean on the scores for both movies. Wow, the mean is the same at 7.33. Kind of hard to make a decision here based solely on the mean. So now you look at the measures of dispersion, in particular the minimum, the maximum, and the range, which are also the same for both movies, ranging from the minimum score of 1 to the maximum score of 10. So no help here. Now it's time to calculate the standard deviation for the two data sets. Okay, now we see a difference. The standard deviation for the first movie is higher than the standard deviation for the second movie, 3.570 versus 1.456. This tells you that there is more variation in the scores for the first movie. The scores are all spread out than in the second movie, where the scores are much closer together. Indeed, if you graph the data, you'll see that there is much more consistency in the scores for the second movie. The majority of your friends rated the movie at a 6 or better, and only 2 were unhappy with it. For the first movie, however, it looks like your friends either loved it or hated it. So if you're only going to go see one movie, I'd recommend the second one, as it looks like it's a safer bet that you will like that second movie. Another example, assume an airline is designing a new aircraft and is looking at seat size. At this time, the average economy seat width is 17.8 inches. They know that they can't provide seats that all 100% of their passengers will fit in, but they want to be able to accommodate most of their potential air travelers. As airlines want to make a profit, their mission is to answer the question, what is the most cost-effective seat size? If they know the mean size of air travelers, likely determined from a sample of air travelers, and the standard deviation of the sample of air travelers, then they can design their seats accordingly. If the airlines want to accommodate about 68% of their passengers, then they would design their seats to accommodate people based upon the average size plus 1 standard deviation. If, however, they want to accommodate about 95% of their potential passengers, they would design the seat based upon 2 standard deviations of the mean. Look, a real purpose for statistics. Processing time. What do measures of dispersion do? Well, they display the range and variability of scores. What are the most common measures of dispersion? Well, the easy ones are the range, the minimum, and the maximum. But there's also variance, standard deviation, and z-score. What do variance and standard deviation do? They tell us how scores are spread out from the mean. The higher the number, the more spread out the distribution is, while the lower the number, the more compressed the scores are. With your basic understanding of measures of dispersion, it's time for you to pull out your calculator and start calculating them.
Okay, go back to the PowerPoint. Okay, just to let you know, since we're in Canada, I call them Z scores, not Z scores. Just in case you're wondering, when I talk about Z scores, you'll know what it is. So, the idea of dispersion is important in the studies of workers' wages, prices of commodities, standards of living of different people, the distribution of wealth, distribution of land among farmers, that should be farmers, not framers, and many other fields. So a brief definition of dispersion: the degree to which numerical data tend to spread about an average value is called the dispersion or variation of the data. The dispersion or variation may be defined as a statistic signifying the extent of the scatteredness of items around a measure of central tendency. And the dispersion or variation is the measurement of the size of the scatter of items, series, about the average. So everything is always coming back to the mean. You want to see how much variation is there about the mean. So that should be your central, as I explained at the beginning of class. These are the most important features of statistics. Everything else comes out of this, because what you're actually doing is measuring the differences in means between populations, between samples, whatever you're measuring. Okay. So just sort of a quick review there. Measures of dispersion. The location, such as the mean or the median, only describe the center of the data, and it's valuable from that standpoint, but it does not tell you everything about the spread of the data. That becomes also important. So for example, if your nature guide told you that the river ahead averaged 3 feet in depth, would you want to wade across on foot without additional information? Probably not. You'd want to know something about the variation in the depth. And a second reason for studying the dispersion in a set of data is to compare the spread in 2 or more distributions. Let me just, okay. So we have the range, the formula, these are the formulas for the range, but remember all the formulas are there for you. The range equals the largest value minus the smallest value, and it can tell you what the spread is. That's what the range is telling you, what the spread of the data is. The mean deviation is the sum times the population x minus, or sort of the mean, the population minus the mean of the sample over n. And the variance is, you see the sigma squared is the sum of the population minus mu n squared divided by n. Okay, but remember you have a formula sheet, so these are all within the formula sheet. So an example, mean deviation. Oh, sorry, I got to make it a little smaller. The number of cappuccinos sold at the Starbucks location in Orange County Airport between 4 and 7 p.m. for a sample of 5 days last year were 20, 40, and 50, 60, and 80. You determine the mean deviation for the number of cappuccinos sold. So, let me just make it a little bigger so you can see it. Okay, there's the formula. We add up all the numbers, divide by the number of observations, we get 50. Then you subtract the mean from each of the observations and convert to positive if difference is negative. And then sum the absolute differences, the absolute, which are positive, found in step 2, then divide by the number of observations. Okay, so on the left-hand side, you have the number of cappuccinos sold daily. You have the number sold minus the mean. Okay, we get these numbers, minus 30, minus 10, 0, 10, and 30. This is the absolute deviation, so this should always be positive because you're taking the absolute value of negative values as well. And you have a total of 80. So the deviation is the total of the deviation divided by the number of observations, 5, is 16. That is your deviation. Okay, so let me just get to the video here. Sorry, it's slow. Oh, for God's sakes. Sorry, I'm getting held up here. Any questions?
Hey everyone, welcome back to Wrath of Math. In today's video, we'll be going over how to find the mean deviation of a...
Sorry about that.
Math. In today's video, we'll be going over how to find the mean deviation of a set of data. The mean deviation is sometimes called the mean absolute deviation or the average absolute deviation. So we're coming here hoping to learn about those. That's what we're talking about. This is a viewer requested video. If you have any requests, be sure to leave them down in the comments. With that said, let's get into it. And here is our sample data set. And this could be data for whatever you want. We could say that this is data collected on the number of pizzas that people eat in a week. And our goal, of course, is to calculate the mean absolute deviation, or just mean deviation, of this set of data, sometimes abbreviated as MAD, just to keep things nice and short. So what is mean absolute deviation? Why would we be interested in finding such a thing? The mean absolute deviation of a set of data basically tells us how much variation there is in the data. It tells us, on average, how much the values in the data set deviate from the average of the data set. But in order to figure out how much these data points deviate from the average, we need to find the average. We could calculate the average of the data set as the mean, or median, or mode. Which of these you select will affect the rest of the process. But it seems to me that the mean is the average most commonly used. That's the one we're going to use in this video. Of course, that's why mean absolute deviation is in the title, because we're using the mean. So the first thing we need to do is calculate the mean of this data set. You might remember we do that by adding up all of the values and then dividing that by the total number of values. So let's calculate the mean, and we'll call it x bar. So x bar is equal to 4 plus 7 plus 5. So we add up all of the data points, and then we divide by the total number of data points. There are 1, 2, 3, 4, 5, 6, 7, 8 total data points. So we divide the sum of the data points by 8. Then adding all of these values up, that gives us 24. That's getting divided by 8, and that is equal to 3. So the mean of this data set is equal to 3. Remember, we're calling the mean x bar. So now we have the mean. Remember, we're trying to find the mean absolute deviation, which tells us on average how much the values in this data set deviate from the mean. Now let's say we have a generic value from our data set. We'll just call it x. How do we calculate the distance between x and the mean x bar? To do that, all we have to do is take the absolute value of the difference of those two numbers. So this is the absolute value of x, our data point, minus x bar, the mean. And it tells us how far away these two values are. And of course, we could calculate this distance for each value in the data set. We could calculate how much each value deviates from the mean. The mean absolute deviation is the average of those deviation values. It's the average of how much each of these data points deviates from the mean. So to calculate that, all we have to do is find this value for all of our data points, add them all up, and then divide by the total number of data points. It's just like calculating the mean of a different set of data. And if we wanted to write that using symbols, we could write it like this. This is the generic formula for the mean absolute deviation of a data set. This character here is a capital sigma. It tells us to add up the distances between all of our data points and the mean. So we add up all of the distances, but then since we want the average distance, we have to divide by the total number of distances. We calculate a distance for each data point. So since n is the total number of data points, we just divide by n. Now let's shrink this a little bit and move it over to the side and calculate the mean absolute deviation for our example. So the mean absolute deviation is equal to the absolute value of the first data point, 4, minus the mean, 3, plus the absolute value of the next data point, 7, minus the mean, 3, plus the absolute value of the next data point, 3, minus the mean, 3, and so on. So this is the numerator. We added up the distance between each data point and the mean. And then we just divide by the total number of distances, which is the total number of data points, which we already know is 8. Let me rewrite that 8. That's kind of gross. 8. All right, now let's move this up one line and finish the calculation. So this is equal to the absolute value of 4 minus 3. That's 1, plus the absolute value of 7 minus 3, that's 4, plus the absolute value of 3 minus 3, that's 0, plus the absolute value of 5 minus 3, and that is 2. And then, of course, this is getting divided by 8. So now what's this equal to? Well, adding up all the numbers in the numerator gives us 14. It's being divided by 8, and we can simplify this. Reducing by a factor of 2 gives us a final answer of 7/4, or 1.75 for those of you who prefer decimals. And I'm going to rewrite that 7 too, because that was a bad 7. There we go, it's a little better. 1.75. So that's it, folks. That's the mean absolute deviation.
So I just want to check with people. Is there anybody that is not follow what he did to come up with the mean absolute deviation? Everybody understand what he did there and how he got the number? Okay. Yeah, it looks like everybody understood the steps that he went through. Remember, you can always look at this video over and over again if you'd like.
It's a measure of how much, on average, the values in a data set deviate from the mean. We calculate it by first finding the mean of the data set. Then we add up the distance between each data point and the mean. Remember that we find distance by taking the absolute value of the difference of each data point and the mean. But then, since we want the average of those distances, we divide by n the total number of data points, which is also the total number of distances. And then it's just straight computation all the way to the answer, 1.75 or 7/4 in this case. If the mean absolute deviation of a data set is small, that tells us that the mean of the data set is a pretty good representation of what a typical point from that data set looks like, because a small mean absolute deviation tells us that on average the values don't deviate much from the mean. But on the other hand, if the mean absolute deviation is large, that tells us that the mean of the data is not a very good representation of a typical data point from that set, because a large mean absolute deviation tells us that on average values deviate quite a bit from the mean.
Okay, so remember, just like when the graphs were shown, you want your deviation to be small. And then you know that the data is clustered around the mean. Whereas if your deviation is large, you know that it's more spread out. And as said in the video, the mean really doesn't represent the population. Okay? So that is one of the most important points about when you're finding the deviation and how relevant it is to the mean.
So then how do we know if a mean absolute deviation is small or large? Well, oftentimes we want to find the mean absolute deviation of a data set in order to compare it to the mean absolute deviation of another data set. Then by comparing the two mean absolute deviations, you can get a better idea of which one is relatively large and which one is relatively small. So here is another data set, and I encourage you to try to find the mean absolute deviation of this data set and then compare it to the mean absolute deviation of the other data set. And let me just make this comma here a little longer. That's not a decimal point, that's a comma. So try to find the mean absolute deviation of this data set. Let me know how it goes in the comments, and I'll leave the answer in the description. One last thing, people don't always use the mean for this calculation. Sometimes people want to calculate the median absolute deviation. Calculating the median absolute deviation, or even the mode absolute deviation, is a little bit different than this. And on top of that, there are even more ways to measure the variation in a set of data. But we'll save all of that for another lesson. For now, I hope this video helped you understand what mean absolute deviation is.
Okay, let's just go back. All right. variance and the standard deviation. We've talked about it a little bit in the other videos. And the variance, the definition is the arithmetic mean of the squared deviations from the mean. The population variance is sigma squared over the sum of x minus mu, that's the population mean squared, over the population the population size. And the standard deviation is the square root of the variance. So sigma squared is the population variance. Sigma is the lowercase Greek letter sigma. It is read as sigma squared. Usually in most statistics problems, the variance is not usually asked for. It can be asked for. It's the standard deviation that's usually asked for, because what are you doing? When you use standardization, what it does is it tries to make your data look like a bell curve. So if you are comparing two completely different populations, you can compare them by standardizing them and finding the standard deviation. So I don't know if people have ever heard the term, oh, you can't compare apples and oranges. Well, you can't compare apples and oranges because it depends on what you want to compare. You want to compare them as, you know, how many are processed during the year, not, you know, what they consist of, because that's different. So you certainly can compare them by using the standard deviation. And large X is the value of an observation of the population. Mu is the arithmetic mean of the population. And capital N is the number of observations in the population. The variance and the standard deviations are non-negative and are zero only if all observations are the same. And for populations whose values are near the mean, the variance and the standard deviation will be small. And for populations whose values are dispersed from the mean, the population variance and the standard deviation will be large. The variance overcomes the weakness of the range by using all the values in the population, because the range only covers the max to the minimum, okay? Whereas the variance does the whole population. So let me get the video for this.
Let's look at measured variability.
Sorry, I got to go through this process. Take a nap, whatever you want to do. Any questions on what we've done here? Not so far. Everybody's getting it? Okay. As I said, chapter 3 is basically the most important because everything else comes from measuring the mean. All right.
The variability or dispersion of a variable is often important in practical situations. For example, packaged food producers want to put a consistent amount of product into each package. They would like little variability in the weight of the product. And the variability in a stock's price is a very important factor in pricing stock options. There are many different measures of variability, and let's start with a simple one, the range. The range is the difference between the largest and smallest observations, or in other words, the maximum minus the minimum. Consider this full of 4 observations. This first value we'll call x1, second one x2, third one x3, and the fourth one x4. The range is the maximum value, 68, minus the minimum value, 45, which works out to 23. The range is pretty easy to calculate and interpret, but it's not a great measure of variability. The range doesn't tell us anything about the spread of the values between the maximum and the minimum. Better measures of variability are based on the deviations from the mean. Every observation has a deviation associated with it. The deviation is simply the value of the observation minus the mean. For this sample of 4 observations, if we calculated the mean, we'd see that the mean x bar is equal to 57. And if we subtract the mean from each one of those observations, we get these 4 deviations, minus 12, 7, 11, and minus 6. Let's plot those and have a look. Here are the 4 observations in a dot plot. The mean of 57 is indicated by this line. We can see here that 45 is 12 units less than the mean, 51 is 6 units less, 64 is 7 units greater than the mean, and 68 is 11 units greater than the mean. The deviations are the signed distance from the mean. Note here that if we add all of these deviations, we end up with 0. The negative values and the positive values cancel out, and we end 0. This is true for any data set. The sum of the deviations is always 0.
Okay, this is one of the important points. Remember that if you get a problem and you add up all the deviations that you've figured out, if it's not 0, then your calculation is incorrect. Because for any data set, the sum of the deviations is always 0. So you're going to have negatives, you're going to have positives, and they should always add up to 0.
So adding the deviations doesn't make a lot of sense, but the deviations are still useful quantities. When we're interested in the variability of the observations, we don't care about the sign, we care about the distance from the mean. So one option that might come to mind is to ignore the sign and work with the absolute value of the deviations. So let's look at that. The mean absolute deviation is the mean of the absolute value of the deviations, or in other words, the average distance from the mean. Let's go back to the data and calculate the mean absolute deviation. Here again is a table with the deviations and the absolute value of the deviations. If we add the absolute value of all the deviations, we get 36. And the mean absolute deviation is the sum of those absolute value of the deviations, 36, over the number of observations, 4, and that is 9. On average, these 4 values are 9 units from the mean. The mean absolute deviation is a nice simple interpretation, the average distance from the mean. But it is not used very often. It is a useful descriptive measure of variability, but it is not used very often in statistical methods. Instead of working with the absolute value of the deviations, we usually work with the squared deviations. It's not obvious as to why we would choose to do that, but methods based on the squared deviations just work a little better. The sample variance S squared is the sum of squared deviations divided by n minus 1. We will use the sample variance S squared to estimate the population variance sigma squared. You might ask, why divide by n minus 1 instead of n? I'm going to gloss that over a little bit for now and state simply that dividing by n minus 1 results in a better estimator of the population variance sigma squared than if we were to divide by n. If you want to know more, I look at that in greater detail in another video. We can think of the variance as the average squared distance from the mean. The units of the variance are the square of the units of the variable. So if we are taking measurements in meters, then the variance has units of meters squared. To get back to the same units as the variable, we often take the square root of the variance. Let's look at that. By definition, the standard deviation is the square root of the variance. The sample standard deviation S is the square root of the sample variance S squared. The standard deviation is the same units as the variance. So if we are taking measurements in meters, then the standard deviation has units of meters. Both the variance and standard deviation are at least 0. S squared is bigger than or equal to 0, and S is bigger than or equal to 0. And they're only going to be equal to 0 if every observation in the data set is equal. The larger the variance or standard deviation, the greater the variance. Let's go back to our data. Here are the deviations once again, and the squared deviations. The variance formula tells us to square the deviations, sum them, and divide by n minus 1. Here, if we added these squared deviations, we see that they sum to 350. And so the variance is equal to 350 over 4 minus 1. And that works out to 116.6 repeating. The standard deviation S is simply the square root of the variance, so the square root of 116.6 repeating, and that works out to 10.8 when rounded to 1 decimal place. Recall that we calculated a mean absolute deviation of 9. The standard deviation is always a little bigger than the mean absolute deviation. How much bigger depends on the shape of the distribution of the variable. So I can't give you a simple rule related, but the standard deviation will be bigger than the mean absolute deviation. Here's a histogram representing the birth weights of 1,000 randomly selected Canadian boys. I've drawn in the mean at 3,433 grams. We cannot determine the precise value of the mean or any of the other values I'm about to give just from the histogram, but I went back to the original raw data and calculated a few important quantities. The hope is that we get a bit of a feel for what these quantities mean in a distribution of values, and perhaps through time we can learn to roughly estimate these values from a histogram. The mean absolute deviation here is 454 grams. Coincidentally, that's a pound. On average, these babies are 454 grams away from the mean. The variance is 379,254 grams squared. The standard deviation is the square root of that, which works out to 616 grams. The standard deviation is a fair bit bigger than the mean absolute deviation for this data set. Because the variance and standard deviation involve the squared deviations, they can be sensitive to extreme values. Very large or very small values can tend to inflate the variance and standard deviation. And here we do have some extreme values out here, left tail. Interpreting the variance and standard deviation is not all that easy. The variance is the average squared distance from the mean, and the standard deviation is the square root of that. So the standard deviation is the square root of the average squared distance from the mean. But that's tough to interpret. So let's look at something that might help us interpret the standard deviation. To interpret the standard deviation, it can be helpful to think of the empirical rule. The empirical rule is a rough guideline for mound-shaped distributions. Distributions that are bell-shaped or approximately normal, like the distribution we see here. We run into this type of distribution frequently. The empirical rule states that for mound-shaped distributions, approximately 68% of the observations lie within one standard deviation of the mean. Approximately 95% of the observations lie within two standard deviations of the mean. And all or almost all of the observations lie within 3 standard deviations of the mean. Let's see what this looks like on a plot. Here's a mound-shaped, approximately normal distribution. And I've cooked the book such that the mean is equal to exactly 50, and the standard deviation is equal to exactly 10. Here, the empirical rule tells us that from 1 standard deviation below the mean, or 40, to 1 standard deviation above the mean, or 60, we would expect to see approximately 68% of the observations. The empirical rule tells us that from 2 standard deviations below the mean to 2 standard deviations above, or from 30 to 70 in this case, we would expect to see approximately 95% of the observations. And the rule tells us that from 3 standard deviations below the mean to 3 standard deviations above, or from 20 to 80 in this case, we'd expect to see all or almost all of the observations. We see here that there are a few observations outside of 3 standard deviations from the mean, but it's a very small percentage of the values. The empirical rule can give us a bit of a feel for what the standard deviation means in terms of the dispersion of the variable. A few notes to finish. Here's the sample variance formula once again. There is an alternative formula that is sometimes used. It is an equivalent calculation formula, and it can help to reduce round-off error in hand calculations. It can help to use this formula from time to time, but these days it's not used as often as in the past because we often rely on software or calculators to carry out the calculations. And this formula up here is a little bit more intuitive. And on that note, I strongly recommend that you learn to use software or your calculator's pre-programmed functions to calculate the variance and standard deviation. It's useful to go through these calculations once or twice to get a feel for what the variance and standard deviation mean. But once we know how to do the calculations, it's best to offload the calculation burden to software or a calculator. And that's a brief introduction to measures of variability.
Okay. So I'm going to go back to the PowerPoint. Okay. So the population variance and the population standard deviation. So here's an example. The number of traffic citations issued during the last 5 months in Beaufort County, South Carolina is reported below. Let me just make that bigger. So you have January to December, and below are all the citations. And what is the population variance? First, you calculate the mean. You find the difference between each observation and the mean and square that difference. You sum all the squared differences found in step 3. Divide the sum of the squared differences by the number of items in the population, and we end up with a variance of 124. Okay? Remember here we're figuring out the variance in the population. Standard deviation. We have the number of citations. We have the number minus the mean. We square it. This is our results. Okay? So we're just finding the variance. We have 1488. Pretty simple to do this calculation. Okay, another couple of examples. We have the sample variance and the standard deviation. The hourly wages for a sample of part-time employees at Home Depot are $12, $20, $16, $18, and $19. What is the sample variance? Okay, so here's the wages. Here are the wages minus the mean. Okay, and then the squared to find the variance is 40. The variance here, S squared equals 40 divided by 4 is $10 squared. That's the variance. Okay, and if we take the square root of the $10, we get 3.33 something repeated, and that's your standard deviation. All right, relatively straightforward calculations. Okay. Does anybody know how to pronounce this name? Anybody? Nobody knows how to pronounce that name?
Bishops.
Sorry, what did you say?
Chebyshev's.
Yeah, that's close. It's Chebyshev. I guess anybody Russian in the class? No, no, we don't have no Russians. Okay. Chebyshev's theorem. Okay, and the empirical rule. So basically what you've seen in the videos where you're talking about the empirical rule, it's used specifically for bell-shaped frequency distributions, where approximately 68% of the observations lie within plus and minus 1 standard deviation of the mean. About 95% of the observations will lie within plus and minus 2 standard deviations, and practically all, 99.7%, will lie within plus and minus 3 standard deviations of the mean. Okay, and Chebyshev's, the arithmetic mean biweekly amount contributed by Dupree Paint employees to the company's profit sharing plan is $51.54. Standard deviation is 751. At least what percent of the contributions lie within plus 3.5 standard deviations and minus 3 standard deviation, 3.5 standard deviations of the mean? Chebyshev's theorem for any set of observations, sample or population. The proportion of the values that lie within k standard deviations of the mean is at least 1 minus 1 divided by k squared, where k is any constant greater than 1. So in this case, we have 1 minus 1 over k squared equals 1, minus 1 over 3.5 squared, 3.5 your standard deviation squared equals 1, minus 1 over 12.25, which is 3.5 squared, equals 0.92. So that is the percentage of contributions that lie within plus 3.5 standard deviations. Basically, that Chebyshev's theorem, just for more detail, we'll look at the video here.
This is Stephanie from Statistics How To.
Okay.
.com, and in this video tutorial I'll be showing you how to use Chebyshev's theorem. In a normal distribution, 68% of your results will fall between 1 and minus 1 standard deviations away from the mean. That's this pink area right here in the middle. About 95% of your observations will occur in this area here between 2 and minus 2 standard deviations from the mean. But what happens if you have a different distribution, say a left skewed distribution? This is a left skewed distribution right here. You can't use that same logic. You can't say, well, here's the mean sort of in the middle, and therefore 68% of my observations will appear here. That doesn't work at all. That's why we use something called Chebyshev's. Chebyshev's theorem tells us that we can use this formula, 1 minus 1 divided by k squared, to tell how many observations you'd expect to find within a certain number of standard deviations from the mean for any distribution, not just normal distribution. So how does this work? Well, let's try a sample problem. Say we have a left skewed distribution and the mean mu is 4.99 and our standard deviation is 3.13. And the question is, how many observations would you expect to find within, say, 2 standard deviations from the mean? K in the formula stands for standard deviations. So we want to know how many within 2 standard deviations from the mean. K in the formula stands for standard deviations. So we're going to go ahead and enter our standard deviation into the formula. Standard deviations of 2. So you have 1 minus 1 divided by 4, you get 0.75. That means 75% of observations will fall within 2 standard deviations from the mean.
Okay, just so you know, what's important about this is when you're using Chebyshev's theorem, you're using it basically for skewed data, left or right, because you can't use the normal formula for finding the mean and the standard deviation. So that's very important. But in life, very few of the populations are skewed like that. So you're not going to come across it very often, but it's good to know how to use it. Not a very complicated formula, but it's in the formula sheet. So just so you know, that's when you're going to use it.
A couple of notes on when Chebyshev's will not work. First of all, you can only use Chebyshev's to calculate results for standard deviations over 1. So 1 standard deviation or more. If you have less, say if you have 0.75 standard deviations from the mean, you cannot use Chebyshev's. The second reason why you can't use Chebyshev's, if your z-score is more than k, in other words, if k is 2 and you have a z-score of say 2.1 or 2.3, you can't use Chebyshev's theorem. Or you could, but you'll get an answer that just doesn't make any sense. So let's say to use Chebyshev's theorem, statisticshowto.com for more.
Okay. Let me just check something. Okay. So, sorry, one last video and then we'll wrap it up. Okay.
Let's see how we can use the empirical rule for normal distributions. The scores of a reference population on the Wechsler Intelligence Scale for Children, WISC, are normally distributed with a mean of 100 and a standard deviation of 15. We want to find a range of WISC scores which contain 95% of all WISC scores for the population. Let's first draw the distribution for the WISC scores. We know that the scores are normally distributed with mean 100 and standard deviation 15. So let's draw our graph. The center of the distribution will be at 100. Going out 1 standard deviation above the mean, it will be at 115. 1 standard deviation below the mean puts us at 85. 2 standard deviations above the mean will be 130. 3 standard deviations above the mean, 145. 2 standard deviations below the mean will be 70. 3 standard deviations below the mean will be 55. The empirical rule tells us that 68% of observations fall within 1 standard deviation of the mean mu. 95% of observations fall within 2 standard deviations of mu, and 99.7% of observations fall within 3 standard deviations of mu. We were asked to find a range of WISC scores contain 95% of all WISC scores. So using the empirical rule, we know that we need to go out 2 standard deviations in each direction from mu. 2 standard deviations above the mean of 100 puts us at 130. 2 standard deviations below the mean puts us at 70. So this range contains approximately 95% of all observations on the WISC score. And we have that 95% of all WISC scores are between 70 and 130 when the scores are normally distributed with mean 100 and standard deviation 15.
Okay. So that was quick. And sorry. All right. Okay, so we'll stop there for now. And if you hadn't had a chance, I'm sorry I sent out the announcement today instead of yesterday. We will finish chapter 3 on Friday. And so test 3 will be available at 5 p.m. and you will have until Monday at 5 to complete it. And when we finish chapter 3, we will begin chapter 4. Also on Friday, I will give you the homework for chapter 4. And I said that your homework for chapter 3 is due at Friday, 5 o'clock. So remember to send that to me. And tomorrow I'll have office hours from 10 to 12. So if you have any questions so far about what we're talking about, and as I remind you again, I will remind you all the time, chapter 3 is extremely important so that you understand the concepts. If you don't understand the concepts, please come to the office hours and we can talk about it. Okay? Any questions from today? If there's no questions, okay, have a good evening, and I may see some of you tomorrow, but I'll see you all on Friday. Okay, take care and stay safe. Okay, good evening.